A new unsupervised and supervised PCA의 3편의 세 번째 동영상을 올리겠습니다. Kernel PCA. The PCA is a linear method because the projection is linear. In case the data points exist on a nonlinear submanifold, the linear subspace running might not be completely effective. For example, see figure 7 보면은 A가 a 2D nonlinear manifold where the data exists in a 3D original space. B, as the manifold is nonlinear, the geodesic distance of points on the manifold are different from the Euclidean distance. B번은 the correct unfolded manifold where the geodesic distance of points on the manifold have been preserved. C는 applying the linear PCA which takes Euclidean distances into account on the nonlinear data where the found subspace has ruined the manifold, so the faraway red and green points have fallen next to each other. In order to handle this problem of PCA, we have two options. 첫 번째가 we should either change PCA to become a nonlinear method or we can leave the PCA to be linear but change the data hoping to fall on a linear or close to linear manifold. Here we do latter. 두 번째. So we change the data. We increase the dimensionality of the data by mapping the data to feature space with a higher dimensionality, hoping that in the feature space it falls on linear manifold. This is referred to as a blessing of dimensionality, which is for sure using kernels. This PCA method, which uses kernel of data, is named kernel PCA. Kernels and Hilbert space. Suppose that the phi vector x vector is a Hilbert space is a function vector which maps the data x to Hilbert space feature space to pi vector is called a Fooling function. In other words, x is phi. Let T denote the dimensionality of the feature space. There is phi x t-dimensional while x is d-dimensional. Note that we usually have t much larger than d. If psi denotes a set of points that is x in and psi, the kernel of two vectors x1 and x2 is x phi x is r and is defined, which is a matter of similarity because the inner product captures similarity. Two vector inner product. We can compute the kernel of two matrices x1 d by n1, x2 d by n2. We have kernel matrix, so-called gram matrix or Gramian, n by n2 kernel x1 is the phi x1은 t by n1이고, it's the matrix x1 to a feature space. The phi x to t by n2 is defined similarly. We can compute the kernel matrix with data set x d by n over itself. 그래서 이렇게 해서 phi는 이렇게 되네. It's full mapped data. Note that in kernel methods, the full data phi x are usually not available, and merely the kernel matrix large K x, x, which is the inner product of pooled data with itself, is available. For well-known kernels, linear, polynomial, 가우시안 혹은 RBF라고 그러죠. KX는 이렇게 되고, 그 다음에 시그모이드, 이게 하이퍼볼릭 탄젠트 펑션. where C1, C2, C3 sigma are scalar constants. The Gaussian and the sigmoid corners are also called radial basis function. Radial basis function, yeah? Radial basis. And hyperbolic tangent, respectively. Note that the Gaussian corner can also be written as exponential. It is noteworthy to mention that in the RBF corner, the dimensionality of the feature space is infinite. The reason lies in the Magnolia series expansion, Taylor series expansion at 0 of this kernel. 여기서 R은 이렇게 defined, which is infinitesimal dimension with respect to R. If we want full data phi x to be centered, center 시경 h는 이렇게 돼. 1벡터는 이렇게 되고. We should double center the corner matrix because if we use a centered full data in equation 52. 52 왜 그래? We have 되고 the corner matrix which is double centered corner matrix KX는 이렇게 파이스 되는 것이고 projection of the training data in the corner PCA는 다음 동영상에 올리겠습니다. 감사합니다.